Now let's start to solve this problem. This is problem 27 of your textbook, which says that a block of mass m, this mass, its mass is m, on a horizontal circle against the wall of a cylindrical room of radius r. This is a cylindrical room of radius r. And due to some initial force, the block started sitting inside the room, pressing against the wall. The floor of the wall is smooth. That means there is no friction between the wall and between the block and the floor. So let's put it there, put it here. There is no friction wall between the block and the floor. This is one point to be remembered. But the friction between the wall and the block is mu. But there is a friction between the wall and the block. Between the wall and the block, there is a friction mu. The block is given an initial speed v naught. As I said, let's say somehow it started moving, somebody pushed it, and it started with the initial velocity v naught. Now, as a function of speed v, now when it has started moving with v naught, and it will continue to move around the wall, touching the wall. But because there is a friction between the wall and the block, the acceleration of the block, the speed of the block will start reducing. There will be a retardation. So that also we know, since there is a friction wall and the block, since there is a friction between the wall and the block, there will be a retardation. That means the block will gradually slow down and finally come to stop. Now, and say the speed at time t is v. Okay, at any time t, the speed is v. Then the question is the normal force by the wall on the block. That is very easy. Since the block experiences a centripetal force, number A, the block experiences a centripetal force equal to, the centripetal force we know is mv square by r. At any time t, the velocity is v, centripetal force is mv square by r. So, the force is equal to The normal force is mv square by r. So this is the answer they wanted. This is the answer they wanted. What is the force? They wanted the force only. B. The frictional force by the wall. Now, since the normal force is mv square by r, normal force is mg square by r. Therefore, frictional force Fs is equal to mu m square by r. This is also done. Then they want the tangential acceleration of the block. Tangential acceleration. Now, there will be a retardation. And I should say the tangential, very clear, tangential acceleration is divided by tangential force by tangential force. And what is that tangential force? Is mu mv square by r. Mu mv square by r. And we know acceleration is the force divided by bars. And here the acceleration is negative. So tangential acceleration is minus mu m v square by r. Let's say this tangential acceleration A. This is the tangential acceleration. Last question. Integrate the tangential acceleration so and so to obtain the speed of the block after one revolution. This is part D. Now, as we have seen, due to the friction with the wall, the speed of the block will start gradually reducing due to this negative acceleration. So we go to the kinematic formula. If acceleration is given, total path is also given. Total path is 2 pi r. We can easily find out the tangential, find out the speed of the block after one revolution. Find it out. What do? We start this way. We know that acceleration A is equal to minus mu m v square by r. Now, let me point out one thing. The question has said, integrate the tangential acceleration. In fact, there are other easy methods of finding out the speed at the end of one revolution. One revolution is the total path. Total path is 2 pi r. So if we go to the kinematics, S is equal to 2 pi r. S is equal to 2 pi r. Initial velocity is equal to v0 given. So by kinematic formula, we can easily find out the speed at the end of 2 pi r. But here in this question, they wanted you to integrate the tangential acceleration. So we'll go into integration. A is equal to minus mu mv square by r. And so we can write A, or acceleration, is always dv dt. That means time domain differential of the velocity. And by using the common method of differential calculus, dv dt can be written as dv ds multiplied by ds dt. Now, so it can be written this way because I just multiply numerator and denominator both by ds. This can be written as ds dt. This is equal to, now what is ds dt? Time domain differential of displacement ds is always v. We always v or velocity multiplied by the dv ds remains here. dv. That means this acceleration a, from here we find, therefore acceleration a is given here minus mu mv square by r. Acceleration will not have the, this is the tangential force. Acceleration will not have the term m. This is a mistake. Acceleration will not have the term. It is mu v square by r. Therefore, here also, acceleration will not have the term m. Acceleration is mu v square by r. Therefore, mu v square by r is equal to, on the right hand side, I have here v into so by cross multiplication, we can find out mu v square ds square ds is equal to, acceleration was negative here, equal to minus rv minus rv into dv into minus rv into dv. By cross multiplication, I can find it here. So from here, we go to the next step. So mu v square, here these two gets cancelled and I have only one v left. So we have ds is equal to, therefore, ds is equal to minus r dv by mu v. So minus r by mu v in dv. Now, here it is dv and v is here. So we should write it this way, minus r by mu and dv by, so that we can integrate it easily. Now on the left hand side, I have ds, the differential of s. On the right hand side, I have dv. Now what we can do, by integrating both sides, by integration, what we find, integration of ds is s, minus r by mu is a constant, minus r by mu is a constant, and integration of 1 by dv is natural log of v that we have seen in differential equation formula, plus there will be a constant, say there is a constant k. Now we have to find out the value of k. Now, in integration differential, you have seen the constant you have to always find out by setting some known boundary condition. What is the known boundary condition? It is at s equal to 0, when it has just started, the v was v0. That is known. So we write at s equal to 0, v was v0. That is given in the problem. So if we put this value here, therefore 0 is equal to minus r upon mu, minus r upon mu is equal to minus r upon mu, natural log of v0, natural log of v0 plus constant k. From this we find constant k is equal to r upon mu, natural log of v0. This is one conclusion. Now we have to just put the value of k in our equation of S. So if we put the value of k in our equation of S, we put the S is equal to minus r upon mu, natural log of v plus k is given r upon mu, natural log of v0, r upon mu, natural log of v0. So if you take minus r upon mu outside the bracket, what you have inside is natural log of v, natural log of v minus natural log of v0. Now, this is equal to minus r upon mu, and natural log of v minus natural log of v0 is equal to natural log of v by v0. This is one conclusion. We have not yet reached the answer. So, natural log of v by v0 will be equal to mu s, will be equal to minus mu s by r. I need a little bit more space here. So let me do one thing. Let me take a little bit of space which is available here to complete the problem. Otherwise, I will have to go to the next page. From here, I go to this space. When I go to this space, I find from here, I find that natural log of v by v0 has gone a little bit downward. Our last equation was natural log of, this was the last, s equal to this. So let me rewrite this again. That will be easier. S equal to, I find, minus r by mu, minus r by mu, natural log of v by v0. From here, what I find? From here, I find natural log of v upon v0 is equal to minus s mu minus mu s from here I find natural log of is minus mu s divided by r, minus mu s by r. So if natural log of v by v0 equal to minus mu s by r, from here the reverse of natural log is exponential power. Therefore, V by V0 is equal to exponential to the power minus mu S by R. Right? Now, the question asks over one complete revolution. That means when S was 2 pi R. When S was in complete one complete revolution, S is equal to 2 pi R. So we put the value of 2 pi R here. So therefore, V by V0 is equal to exponential to the power minus mu by R by capital R. Now this R and this R gets cancelled. So what we find? Therefore we find V is equal to V0 multiplied by exponential to the power minus 2 pi mu minus 2 pi mu. This R got cancelled. So this is the final answer. Okay. Now we go to the next problem. We go to the next problem that also will not be very difficult. I think we can easily solve this. Here, it is said that a table with a smooth horizontal surface revolves with a uniform. That means this table itself, the table itself revolves. The table itself revolves in a circular way with a velocity omega around the point O. This is the point O. At a distance r, this is the distance r from the table as shown in the figure. Second part is a smooth incline AB of angle of length L. Length of the AB is L, where L is very small with respect to the R, is fitted on the table at an angle theta with the tabletop. A small particle kept at the point A. And here, a small particle is kept. Here, a small particle is kept and released to move along AB. Now, why should it move along AB? Here, actually, when the whole table is moving, or I should say, whole table is revolving around O. This small particle will need a centripetal force. Now, here is the catch. Who will provide this centripetal force or who counteracts us? Because the table is smooth and there is no string between the center and the small block. Neither gravitation works because gravitation works only perpendicularly downward. So, in this case, we have to consider the concept of pseudo outward force, which is called centrifugal force, which is called centrifugal force. Concept of centrifugal force. The centrifugal force always works radially outward. Always works radially outward. Now, and there is an incline. So let us draw this small part. This is the table, say, this is the table, and this is the incline at an angle theta. There is the block. This block experiences a centrifugal force which is equal to centripetal force, which is equal to m omega square r. R is the radius of circular motion. Now, this centrifugal force will have a component up along the slope. This component is obviously m omega square r theta. This force upward will try to take this small ball up the inclination. If the inclination is very steep, the ball will not be able to go, will not able to climb. But as you can easily see, if the slope is very small, the block will have a tendency to climb up on the slope. So this is the upward force. Upward along the slope is m omega square r cos theta. So you can say the force upward along the slope equal to m omega square r cos theta. So the upward acceleration is equal to omega square r now with upward acceleration, it will start moving upward. Now, the question is, find the time taken by it to reach the topmost point, B. Now, here, we shall use the kinematic force, kinematic action. That means from here to here, the length is given L, the total length of this L. We shall use the kinematic, and acceleration is omega square r cos theta. So by using the kinematic equation, which says S equal to ut plus half ft square, S equal to ut plus half at square, ut is 0. Rest. Therefore, length L is equal to half A is omega square r cos theta, omega square r cos theta into t square. Square is the time required. From here, we can easily find t square is equal to 2L divided by omega square r cos theta. Therefore, time required by it is equal to whole under root L upon omega square r cos. So this is the answer to this question. Time required for this small block to climb upward is whole under root 2L upon omega square r cos 2L upon omega square r cos theta. Okay? So next we shall go to the next problem.